Welcome to our discussion of naming ionic compounds with transition metals. In this lesson, we'll identify and define transition metals and translate from symbol to name and name from symbol for ionic compounds containing transition metals. So before we can begin naming, we need to understand what a transition metal is, because remember, whenever you're naming compounds, the very first thing you have to do is determine what your elements are within that compound so that you know what naming rules to follow. So if we take a look at our periodic table, we notice that many of our groups have charges at the top, but we have this whole group in the middle that doesn't have any charges above the groups. And this group of elements in the middle are what we call our transition metals. So the reason we call these particular metals transition metals is because they don't have a set or a fixed charge that they're going to take on when they become part of an ionic compound or transfer electrons through an ionic bond. Their charge, or technically their oxidation state, is variable. Their charges will transition based on the element that they are bonding with. All right, now that we know what transition metals are, we can learn how to name them. So we have a couple rules to follow. So the first of which is that our ionic compounds that contain transition metals, the transition metal is always going to be the cation. It's going to come first. And because it's an ionic compound, it's going to be a transition metal paired with a nonmetal. And the charge is going to be given in Roman numerals in parentheses within the name of these compounds, because we have to specify what charge our transition metal is taking on, because we don't automatically know. So we have to give that information explicitly. And finally, like our other ionic compounds, the name is going to end in "ide." Let's take a look at our first example, FeCl2. We can't simply name this iron chloride because we have to communicate what ion iron is acting like in this compound, or what charge iron is taking on. And we know looking at the periodic table for iron isn't going to be any help because there's no charge over iron's group. We do, however, know the charge that chlorine takes on in an ionic compound. So knowing that this molecule is completely balanced, the positive and negative charges balance each other out, so this whole molecule is neutrally charged, we can use the known charge on chlorine to work backwards to figure out the charge that iron is taking on in this particular molecule. So when we look at our periodic table, we see that chlorine always takes on a -1 charge. So if chlorine has a -1 charge and we have two chlorines, then we have an overall negative charge of -2. So that overall negative charge of -2 has to be completely balanced out by the one iron present. So in this case, we know that iron must have a +2 charge in order to balance out the -2 charges of our chlorines. So when we write the name of this compound out, we need to include the charge for iron. So we're going to write it as iron, and in parentheses 2 in Roman numerals, chloride. So the full name is iron 2 chloride, meaning that iron is going to take on a +2 charge in this particular compound. Let's try another example. So here we have Hg2O, so two mercuries bonded to an oxygen. Well, again, our mercury is a transition metal, so we don't know the charge, but we have to include that in our name, so we have to work backwards from oxygen, whose charge we do know. So we know oxygen always takes on a -2 charge in ionic compounds, and we only have one oxygen, so our overall negative charge for this molecule is -2. So our charges on our mercuries need to be able to balance out that -2 charge. Well, I have two mercuries, so that must mean that each of my mercuries has a +1 charge. So the charge that I'm going to write over my mercury is going to be +1. Because remember, the charges on top are the charge that each atom of that element have. It's not the collective charge, it's the charge specific to each atom of that element within that molecule. So if each of our two mercuries has a +1 charge, that's going to totally balance out the -2 charge of my one oxygen. So the name of this molecule is going to be mercury 1 oxide. Remember, the number in parentheses pertains to the charge of the transition metal, not how many transition metals you have. So be very careful. That's a very common mistake. Make sure your Roman numeral is representing charge, not quantity. All right, let's take a look at a couple more examples on your own. Pause the video, try these two, and then when you're ready, hit play to check your work. All right, here you go. For the first example, you should have gotten nickel 3 bromide because we know our bromine has a -1 charge, but we've got 3 of them. So we've got an overall charge of -3. So our 1 nickel has to have a charge of +3 to balance out that -3 charge. And down here, the second example was a little bit trickier. We know that our nitrogens take on a -3 charge, but we have 4 of them. So -3 times 4, and we have -12 for our total negative charge. So our 3 manganeses altogether have to balance out to a +12 charge. So since I've got 3 manganese and I need a +12, then each of my manganese atoms should have a +4 charge because +4 times 3 gives us that +12 that we need. Another shortcut way of doing this is to actually just reverse swap and drop. Take your subscripts, bring them up and move them over to the opposite element, and those are going to be your charges. So for example here, reverse swap and drop, right, that we saw in our naming ionic compounds. If we do the reverse of the swap and drop, we take this 3, we bring it up above the nickel, and that's the charge on nickel. Down here, our nickel, that we know that subscript, even though it's not written, is a 1. So if we bring that 1 up over the bromine, and it becomes the charge over the bromine. And then just remember your cation is positive and your anion is negative. Down here for your second example, the reverse swap and drop works as well. Our 4 from our nitrogen, we move up to be the charge on our manganese, and our 3 on our manganese, we move up to be the charge on nitrogen. So another quick way of doing that is just to reverse swap and drop, and it should give you your charges every time. All right, the very last thing that we need to learn how to do with ionic compounds with transition metals is how to go from name to symbol. So we have to add one more rule in here. We have to be able to balance the charges, and we're going to do that in the same way that we balance the charges for our ionic compounds. We're going to be using our swap and drop method. And it's actually a lot easier than going from symbol to name, which we were doing earlier, because all of the information that we need is already provided. So for this example, copper 2 chloride, we know that the charge for copper from that Roman numeral is a +2. And we can look up the charge of oxygen on the periodic table, and it's a -2. So when we do our swap and drop, our formula becomes Cu2O2. But when we have our subscripts that are the same, we can actually simplify that using the lowest common denominator. And so we can simplify this and it just becomes CuO. Now try these last 2 examples on your own. Pause the video, and when you're ready, hit play to check your work. All right, there you go. For the first one, you should have had AgBr because our charge on silver is a +1, and we know our bromine is a -1, so it's already balanced, so we can just write it as is, AgBr. For the second one, iron 3 oxide, our iron, due to this Roman numeral, has a +3 charge this time, and our oxygen has a -2 charge. So when we swap and drop, we bring this 2 down to our iron, and we bring this 3 down to our oxygen. So we have a formula of Fe2O3. And that concludes our discussion of naming ionic compounds with transition metals. Bring any questions you have with you to class.